afternoon, everybody. Thank you for coming for my completion seminar. So today I'll be presenting my PhD thesis work, which is based, the title of which is Robust Fault-Tolerant Scheduling for Scientific Workflows in Cloud Computing Environments. So we have a presentation outline which will follow the introduction, a brief literature review, contributions, the system implementation, and the conclusion. So before we start, I would like to say why we need workflows. So basically, in the last few decades, the experiment methodology in science has increased vast amounts, mainly because of computational capabilities, which has made the applications more complex, involving large data sets. So we need a scalable and an autonomic way to handle these applications, because of which workflows were developed. Basically, workflows are there in scientific applications, in business processes, enterprise resource planning, customer relations services. In scientific applications, we have medical applications which are there as workflows, disaster recovery applications, astronomy applications. Then we have gravitational physics, a whole large areas of scientific domains can be represented as workflows. So workflows in general are nothing but systems which can automate large complex data analysis, which can help in moving data to compute node or compute to data node, perform these computations, get results, and manage the storage of these results in an automated, seamless manner, making it easier for scientists to do their experiments, get results, analyze the results, collaborate, share the results, and reproduce the results. So the core, if you look what workflows are, it's nothing but a collection of tasks which are either data dependent or control dependent, which can be represented as directed acyclic graphs. And when we speak about workflow scheduling, if you have to put it very simply, workflow scheduling is nothing but mapping n number of tasks to m number of machines, maintaining the dependencies. So before going into the presentation, I would like to just stress upon a few jargons that we will be continuously using. A workflow make span is nothing but the execution time of the workflow, the time it takes to finish the execution. The cost of the workflow is nothing but how much monetary cost that it needs to run these workflow on the resources. A deadline is a user-defined value, which is a time-bound value for the workflow to finish within that time, which is more of a constraint, and budget is similarly the cost constraint of the same. So workflows have been for a very long time. It started with shell scripting, and then it slowly moved on to supercomputers, then clusters and grids, and now it's rapidly moving towards cloud computing. The reason being, in cloud computing, we are able to provision resources on demand. We can configure them dynamically. We can deliver them on demand. It is highly scalable. There's different levels of services that are provided. It is hugely driven by market principles, and it works on a pay-as-you-go model. When we speak about cloud computing, there's different service models that are there, which are software as a service or platform as a service, where there is a deployment. Sorry, something else. So in a platform as a service, the provider gives a platform where the user can develop his application, deploy it without worrying about the underlying infrastructure, how the servers are scaled up, scaled down. In infrastructure as a service, we have computational nodes which are given to the user or the storage network, like virtual machines, the example being Amazon EC2. So here in this thesis, when we speak about cloud, we're generally referring to infrastructure as a service. So when we want to schedule these workflow tasks on cloud computing, which gives us so much tremendous benefit, it also comes with its own bit of challenges that we need to be addressed. And some of the challenges are the performance variation of virtual machines. If we take two virtual machines on the same data center, it does not give us the same performance. Or the same virtual machine at different times of the day gives different performances. or in different data centers, it's giving different performances. So that's a huge issue that needs to be dealt with. And because it's a huge complex infrastructure, it has its own resource failures, virtualization overheads, failures in the cloud, and then because it's a distributed system, it's got its own inherent challenges like network latencies and failures, task level failures, failures in storage, IOs, and workflow management itself. So this is the gap that we are trying to address. So the core or pivotal question that we want to address in this thesis is how to make workflow scheduling more robust for performance variations and fault tolerant to all the failures that are there in the cloud computing environments. So in pursuit of this central question, we have developed a few novel scheduling heuristics. We have developed some resource provisioning policies, some bidding strategies. We have done a thorough performance analysis of these strategies on time, cost, and fault tolerant aspects. We have proposed some metrics to measure the fault tolerance and robustness. We've also developed some resource plugins for multi-cloud environments in our workflow engine. So to start with, we'll just touch upon literature survey, which is currently submitted to ACM Computing Surveys and is under review. So I'll just present the overview of workflow scheduling here. So when you speak about workflow scheduling, the architecture which tells us where the scheduler is placed in a workflow management system, there are typically three kinds. There is a centralized system where the centralized entity schedules everything, and there is a hierarchical system where the central entity schedules the sub-workflows, and the sub-workflow in turn schedules the task. Or we have a decentralized system where the tasks itself have a scheduling component within itself, and it schedules itself. And there is when we speak about planning scheme is how the mapping between tasks and virtual machines is done. So it can be done in two ways, where it is static mapping, where before the execution we map the tasks onto the virtual machine, or it can be a dynamic mapping where as the execution goes, we map the tasks onto the resources. Then when we speak about scheduling heuristics or techniques, we can broadly have techniques which are heuristic, which are dependent on the problem that we are solving, or a more general meta-heuristic kind of solutions where we have genetic algorithms or evolutionary algorithms. And the objective of most of these scheduling components are either time-based, cost-based, energy-based, or quality of service-based, or fault tolerance-based. Because we are trying to address the fault tolerant and robust aspect, we are mostly focusing our objectives on fault tolerant based schedulings. So when we speak about fault tolerant aspects, we need to know what are the fault tolerant techniques that are there currently in the literature, and these are some of the prominent techniques that are already there for workflow management systems. We have replication, where we replicate either a task or a virtual machine, and the more number of replicas gives us more the ability to withstand that many failures. Then we have resubmission, where we retry a resource as many times, as it fails, we retry it on the same resource or another resource. Then we have checkpointing, where we take consistent snapshots of the execution. Then we have providence, which is basically a metadata management, which is used for rescheduling of these workflows. Then we have rescue workflow. Rescue workflow is a technique where we let the workflow run in spite of failures until the point it can execute, and then we take these information for a rerun of the workflow. And then we have user-defined exception handles, where if you anticipate a failure could happen in a situation, we code and alternate the solution for that situation. Then we have an alternate task kind of an implementation, where if we can have two tasks which can take the same input and produce the same output, but say one is computationally intensive but reliable, and the other one is less computationally intensive but less reliable, so we can run the first one, and in case of failure we can switch back to the next task. And then we have failure masking, and slack time. Slack time is basically we have a time buffer to our execution, and then it can tolerate some performance variations or failures. And then we have trust-based, where we give a factor of trust to the resource or the cloud provider itself, and based on which we schedule. So now we move on to the core contributions of our thesis. The first one, this is published in INA, Victoria, which in 2014. here we propose a robo-scheduling algorithm which maps tasks onto heterogeneous cloud resources with the objective being to maximize robustness. At the same time, it is trying to minimize the cost and and the constraints being deadline and budget based. So when we speak about robustness is an idea which gives us the ability of which tells us how much uncertainty the schedule can take while maintaining a stable solution. Robustness alone is not a metric. It is associated with another parameter like length or make span of the solution. It generally gives us an idea of how stable our solution is. It is very much required in time-critical applications, and it is usually achieved with redundancy in time or space. So here we have considered two types of uncertainties. One is task failures, and the second one is performance variations of virtual machines. We measure our solutions with respect to two metrics. One is the robustness probability, which tells us how likely the workflow is to finish within a given deadline, and the tolerance time, which is basically tells us how much time is left between the completion and the deadline, so that it gives us an estimate how much more failures it could further withstand. So here in the scheduling algorithm, what we do is we take the whole workflow and divide it into partial critical parts. I would illustrate that with an example. So if we have a workflow like this, we basically do a kind of a clustering, I could say, of the workflow into partial critical parts. So we have these partial critical parts. A partial critical part is basically a collection of tasks which share a huge amount of correlation between them, and so it minimizes the data transfer time between them. And the idea being we can map the whole partial critical path onto one resource so that it fastens the execution of the workflow. So here we first cluster, or we divide the whole workflow into different partial critical paths, and then we add some slack time to the estimated execution time of the partial critical path to develop a robust solution. So what we do is we have defined 4 types of robustness types, which is basically the amount of slack time that we want to add into these partial critical paths. So we have no robustness type where we don't add any slack time. Then we have a predefined slack time that we add, and then one node failure is the highest execution time in the partial critical path of one task. We add that, and similarly we have 2 node failures. The idea being it can withstand 1 node failure or a 2 node failure. So based on this, we develop an exhaustive solution set where for each VM we have a robustness type and the time and cost associated for that. So once we have a whole exhaustive solution set based on the deadline and budget constraints, we reduce that exhaustive solution set into a feasible solution set. And from this feasible solution set, our idea is to get one solution or one virtual machine type and robustness type to map into the partial critical path. And for selecting from this, we propose 3 policies, which is basically robustness, cost, time, and robustness, time and cost, and a weighted approach. So in the robustness, cost, and time, what we do is we choose the maximum robustness type with next, then we choose the least cost and least time. And similarly for robustness cost, we choose the maximum robustness type and with least amount of time and cost. And in the weighted approach, the user can define his priorities in terms of these, and based on this, based on which we select one solution. So this solution will tell us what is the robustness type, what is the VM type, what is associated partial critical path time and cost. So this heuristic we have tested on 5 state-of-the-art workflows. We've used 10 virtual machine types. We consider data transfer time, but we don't consider data transfer cost. We have tested this with 2 failure models. We have used failure traces, and we also tested with failure probability. We used a checkpointing mechanism, and we have tested it with 2 reference algorithms, which is basically ICPP. And the second one is a robust slack time, which uses slack time as its to make the algorithm robust. So we see that in these graphs that our policy RCT gives us a high robustness time. What we have done here is we have kept the budget fixed and we have varied the deadline, and in that experiment we have kept the deadline fixed and varied the budget, and in both the cases we see that the tolerance time is very good for our solutions. And in terms of robustness probability also, we see that our solutions are giving much better than the baseline solutions that we considered. In terms of make span as well, our solutions are giving very low make spans. In terms of cost, two of our solutions are giving us very good low cost, but the RTC policy performs with a slightly higher cost because we are emphasizing more on the time in that policy. So to summarize, in this solution we have presented 3 resource provisioning algorithms whose objective being is to maximize robustness, minimize make span and cost. We add slack time judiciously to make the schedule robust in this approach. We have tested this with 2 failure models, 5 workflows, and measured it with 2 robustness metrics. And the result of this is we can indicate that the policies make the schedule more robust while keeping the make span minimal with a slight increase in cost. So the next work, we try to use task, retry, and checkpointing mechanism. This was published in ICCS in Australia in 2014. So the first work, what we did was basically a static mapping of tasks onto the workflows. In this, we tried to do a just-in-time adaptive dynamic scheduling. And in the earlier work, we used just on-demand instances. Here we use a combination of spot and on-demand instances. We use an intelligent bidding strategy. And the aim of this is to provide robust schedules, but at the same time minimizing the cost while satisfying the deadline constraint. So I mentioned about spot instances. I'll just give a background of what spot instances are. So Amazon started provisioning its idle or unused data center capacity as spot instances from around 2009, December. So they provision these instances in an auction-like market where you have a spot price for these instances and it keeps varying with time. It can vary for instance types, it varies with region and everything. So the user bids a price for these instances, and if his bid price is equal or more than the spot price, then he gets the instance. So, but the downside of this is, the plus point here is you get the instances at a very cheap price, but the downside being if the spot price goes higher than your bid price, your instance can be snatched away from you. So it's got really low SLAs, but it gives us enormous cost benefits, and some of the applications have shown that it can give up to 60% cost reductions. So the crux of the algorithm that we want to do here is when we have a deadline, we estimate the critical path and we define a time flag which we call LTO. So before this LTO, we schedule all the tasks on the spot instances because they are cheaper, and at this time we can take more risks and we can withstand failures. But as we go closer to the deadline, as we go past the LTO, our risk-taking abilities goes really down. So we need to map them onto on-demand resources which are more reliable. So this is the crux of the algorithm. So here, to estimate the runtimes, we use a Downey's analytical model, and we estimate the failure probabilities of the bid price based on the history of the spot price. So in the scheduling algorithm, what we essentially do is if the current time is before the LTO, before our time flag, then we try to map them onto spot instances. First, we see if there is any free instances that is already there. If we are able to find such instances, we map the task onto that instance. If we don't have, then when we see is the time left to create a new spot instance. If so, we first estimate the bid price for the spot based on a bidding strategy. Then when we have the bid, we estimate what is the failure probability of the bid. So if the failure probability is low, only then we map the spot instance. If we don't have any time, if we have moved past the LTO, then we have to map it onto on-demand instances. When we are mapping into spot instances, we are mapping only on one type of instance because we want to reduce the cost, so we choose the smallest instance. But when we want to map it onto on-demand, we choose multiple instances. So based on how far it is, how close the deadline is, we map it onto the instances which give higher performance. So we select the suitable instances, and based on the suitable instances, we see if there is an already running or existing instance, we map it onto that. If not, we create an instance which gives us the best cost to performance ratio. So earlier I said we estimate the critical path and we decide the time flag, that is the LTO. But we can estimate the critical path based on any instance. So if we estimate the same thing on a slowest instance, we'll have a longer critical path. That means we'll have less time to play around with the spot instances. So for that, we have proposed two variants of the same solution, which is basically a conservative approach and an aggressive approach. In the conservative approach, we estimate the critical path of the lowest instance so that it's more cautious. It uses spot instances more cautiously. And in the second one, we estimate with the highest cost instance so that the critical path is less, so the LTO is further up. So we can play around with spot instances more. The risk-taking ability is higher. So, but as the failures are more often, this approach, at the end, we have to go for more expensive on-demand instances in this approach. Oops. Okay. So I mentioned about a bidding strategy, how we choose the bidding. The bidding strategy, what we do is we take the current spot price, the on-demand price, the failure probability, the time flag, the current time, and we have some alpha and beta values based on which we have developed a function which gives us the bid price based on these parameters. So this is the graph how the bidding price works. If the red lines are the spot instances, our bidding strategy starts with the bid price slightly above the spot instance price, and as we move closer to the deadline, our bid price goes higher and higher, because initially in the initial workflow execution, the risk-taking ability is higher, so we bid a smaller price. But as we go, we don't want the instances to be terminated because of the bid price, so we choose a higher bid price. To compare that, we have other bidding strategies we have proposed, which is an on-demand bidding strategy. We just bids the on-demand price of the instance, or a night bidding strategy, we just bids the current spot price. We have tested this through our CloudSim on a LIGO workflow with 1,000 tasks. We've used 9 different types of VMs for on-demand instances and used one type of spot instance. So we can see that in the results, the cost of our algorithms have come down consistently as compared to the on-demand bidding strategy. But when we compare it with the spot instances, we see that initially when the workflow is tight, the cost is higher, but because it's bidding only in the spot instances, the failure is higher. But ours, we don't have failures, but at the same time, we're able to keep the cost low. But once we go for much relaxed deadlines, actually ours is performing much better than spot instances because we are predicting much better and we are choosing the instances wisely. So this is a demonstration of how the bidding strategies work, and we show that our bidding strategy is able to give better solutions almost at all times. And this is how the task failures happen because it's out of bid failures. Initially, when the deadline is set, we don't play around with spot instances more, so there's not much failures. As the deadline gets more relaxed, we experiment more with spot instances, so there's more failures at that point. We also have done an experiment to show what is the right checkpointing duration, and we check this with no checkpointing with 5 minutes interval, 15 minutes interval, and 30 minutes interval. Overall, we've seen that when we use checkpointing, we can achieve almost 14% reductions in cost. But because the spot prices are quite low, most of the time, 80% of the time, the spot prices are almost like 1 cent or something. We don't see much differences between different intervals. So it's better to choose, say, checkpointing with 30 minutes interval because the overhead is lower. But as and when the spot prices becomes higher, probably the differences would show up then. So to summarize here, we have proposed 2 scheduling heuristics which map workflow onto spot instances and on-demand instances. They minimize the execution cost while providing a robust solution. So we are trying to be the algorithm is robust against out-of-bid failures and performance variations. We also propose an intelligent bidding strategy. So the next contribution is with task replication and task retire. We're trying to extend the work that we have done in the previous chapter. This is currently under review in ACM transactions. So here what we do is we develop a dynamic algorithm which uses spot and on-demand instances. And here we use a combination of fault and fault retry, task retry and task replication model. So when the deadline is relaxed, we use a task retry approach, and when the deadline is strict, we use a task replication model. So, and the goal of this approach is to minimize the execution cost while reducing, while being robust, satisfying a deadline constraint. So we develop a concept called essentially critical tasks. So let's assume we have two scenarios where this is the start of the execution. When we have a deadline, we have an estimated make span, and we have a slack time, that is the time to play around with spot instances. But as the execution goes, once some level of tasks are completed and there are some failures or something, we have a deadline which we have to meet. Then we have some tasks which have to finish by their earliest finish time, the estimated earliest finish time. So these tasks are called essentially critical tasks. So essentially critical tasks are not just critical tasks on a critical path, but they are critical because they have to finish within their estimated finish time. So we replicate these kind of tasks only. So first what we do is similar to our last algorithm. We first try to see if there is already, before the LTO, we try to map them onto spot instances. We first see if there is any available spot instances. If not, we map them onto new spot instances. Or if we have moved past the LTO, we map them onto on-demand instances. And for task replication, when the deadline is really short, as I explained earlier, we replicate the essential critical task. We propose two variants basically here. One variant is we replicate all the essential critical tasks, and the second variant we replicate all the critical tasks. So here we see that our algorithms are consistently have lower failure probabilities compared to our previous algorithm, and then the tolerance time is also higher. The make span is also lower. The make span for the critical tasks are much lower than the essential critical tasks because we do more number of replications here. We also do a resource consolidation here. So because of resource consolidation, we see that the make span is much lower than what it could have been. The cost is higher than than our previous solution. This is because we do more number of replications here. But because of resource consolidation, we receive significant cost reductions in this approach. So finally, moving on to the last contribution of this thesis, which is a system implementation for a multi-cloud framework. So we have extended our cloud-based workflow management system, which is an existing project in our cloud-based lab. We have enhanced the broker to provision resources on demand. Earlier, the cloud-based management system, the resources had to be statically defined. So here we have modified it to provision resources on demand as and when it needs. We have developed an effective fault-tolerant technique. We've also proposed a resource provisioning algorithm for multi-clouds in this method. So workflow management system consists of a workflow portal through which you can compose or edit workflows, or you can also submit an already there workflow. It has the ability for many I/O models, which are basically how the input tasks and the output tasks need to be defined. Then it has a workflow engine which takes the workflow definition and it translates that into task dependencies, input constraints, and it passes it on to the scheduler. The scheduler then schedules these workflows onto resources, and it is done through the resource broker. To manage all these coordination, the workflow scheduling approach looks like this. We have a workflow scheduler which creates task managers for each task, and these tasks, the task manager has the task definitions, the task details. It does the resource provisioning through the resource broker. It also has a monitoring service. And all these, the task manager and the workflow coordinator, they all communicate through the event service. So why we need a multi-cloud system? So when we have a multi-cloud integration, we are able to seamlessly develop the application to multiple cloud providers. So say suppose if we had to provision resources on Amazon, we can provision them. At the same time, if you want to provision at say Windows Azure, we can do that with little changes. Otherwise, we have to develop extensive API sets for each cloud provider. So with a multi-cloud tool like JClouds, we can do that with little configuration changes through all cloud providers. At the same time, each cloud provider has a different pricing model for their systems. So we can take benefit of multiple cloud providers' pricing mechanisms. The billing periods change from each cloud provider to cloud provider. So Amazon prices their instances per hour, but at the same time Azure or Google Cloud prices them at per minute. So based on the task characteristics or the workflow characteristics, we can choose different billing periods. The resource characteristics change between different cloud providers. So we have a wider option to choose which kind of resource suits my task needs exactly. And the other thing is, if we have a private cloud, like we have a OpenStack realization in our cloud lab, so we can deploy our applications there, but because in a private cloud, the resource limitations are less. So when we have more demand or for the extra workload, we can provision them on a public cloud. Then we have regulatory and legal requirements, because when we have a multi-cloud system, these things can be addressed more effectively. So the resource provisioning policy that we have proposed is, first we create a general pool of spot instances, and we try to map the tasks onto these. If we need more resources, then we create on-demand instances on the fly. And if there is no budget, then we try to map them on the existing instances that we have created. So we have tested this with a number of failures. So we have implemented a task retry mechanism. So we increase the number of failures, and we can see that the scheduler is able to map the tasks onto different cloud providers and finish them effectively. Of course, because we use a retry mechanism, the execution time increases slightly, and this graph tells us how the resources are created with respect to time. So this was the application that we did. It was an astronomy application called Montage. So this is the structure of the application, which takes input images as inputs. So it is basically images of the sky, and it creates a mosaic of that input. And this is the final output that we've got from that case study. And that brings me to the conclusion and future direction. So we have proposed novel fault-tolerant heuristics. We've experimented with various fault-tolerant techniques. We have given an extensive literature survey. We've proposed resource allocation policies, bidding strategies, and we've also developed a multi-cloud integration for the workflow management system. So some of the future directions is, people can look into the failure characteristics in clouds, which are not very well studied. There is no unified metrics for fault tolerance which can be developed. Playing around with pricing models, mapping different tasks onto a single instance. Essentially this study is we map one task onto one virtual machine. How about mapping multiple tasks onto a virtual machine? How does that improve the performance? That is something that can be looked into. Workflow specific scheduling. The workflows are becoming more and more specified in terms of either it is compute intensive or IO intensive. So developing scheduling algorithms specific to that, and also looking into multi-cloud challenges could be some of the future directions. These are the list of publications that I've done. And finally, acknowledgements. Firstly, I would like to thank Professor Raj for giving me an opportunity to do PhD under him. It was a wonderful experience, and I would like to thank him for all the coordination and encouragement that he has given us. Then I would like to thank Professor Rao for always being open for discussion and giving so many solutions. And his suggestions have made the thesis more profound. Professor Chris Lakey for generously accepting to be the chair of the committee, giving valuable suggestions at all the review meetings. I hope I have addressed at least most of them. And I would like to thank postdocs Rodrigo, Amir, also Saurabh, for giving valuable feedback on all the works, which has made it more strong. And I would like to thank my collaborators, Saurabh, Mohsen, Maria, for taking time out of their work and helping in my research, and all the past and present cloud members who helped me immensely through all the time, especially Adel, who's been more of a friend, and Shenhao, Yasser, Nick, Atafa, everybody for all the great time I had. My family, my wife, who's been the pillar of my strength.
So wife is not part of the family, really?
Stressing.
I have my punchline.
So that brings me to the end of the presentation. Thank you.